Okay, so hi everyone. Welcome to the first lecture of the K-Theory series organized by the Grothendieck School. As you know, today's speaker is Professor Amit Kuber. The plan of the school must be clear to you by now. Through K-Theory in Totality, we are trying to bring all the K-Theory subjects all together under one umbrella. Of course, you can enjoy one of the particular part that you are interested in, but we would really like you to have an overview of all different branches of K theory and how they're different, how they're similar, and all sorts of stuff. We'll try to portray how K theory is a generalized cohomology theory, at least for topological case. But apart from that, the subjects are beautiful in their own right. Yeah, up to you, Professor.
Thank you, Deepankar. So I have one request, for people who are not lying in their beds. If you can switch on your videos, I'll feel like I'm not talking to an empty room. But people, that's just a request. It's not, obviously, it's not compulsory. Okay, I can see some familiar faces. Okay, so while you are doing that, I mean, this series is called Grothendieck School of Thoughts, and I have been a very big fan of Grothendieck myself. In fact, like not just as a mathematician, but also as a philosopher. And I made sure that my PhD thesis started with the name of Grothendieck. So I also shared one of the quotes of Grothendieck. I mean, he wrote so-called autobiography, this Recall the Sane. I'm currently attempting to translate some pages of it, some beginning pages of it with a friend, from French to English. And well, translation is not really the big component of that, but understanding him as a person, why he was called the greatest mathematician of the last century. And that's really the crux of the issue. So now this particular series is on algebraic K theory, or K theory in totality, but out of that algebraic K theory. But as there are different branches, algebraic, topological, operator theoretics, K theory of schemes, and different types. So one thing is very clear about this, that K theory is not really a subject that grows vertically. Okay, so for example, number theory, you go deep and deep and deep, algebraic geometry deep. You try to go deep in a subject, whereas K theory is a subject which cuts across different sections of mathematics. Okay, so it's a horizontal subject in some sense. So there are connections of K theory with various things, various branches of mathematics, and that's why there are so many different series of lectures in this particular topic. So I'm going to speak about algebraic K theory. I'm not an algebraic K theorist. That's a disclaimer. So during my PhD thesis, I studied algebraic K theory, like K theory of categories, and in particular model theories. So model theoretic structures. However, in the process, I really enjoyed learning K theory, and I have taught this course once. So if you go to my personal webpage, then there is a series. There are lecture notes on introduction to algebraic K theory. My students have scribed that, so take it with a pinch of salt. So not everything has to be correct. I try to make sure most of the things are correct. And before we begin, I should also give you some literature. So the books, the standard books, which I would like to recommend are, of course, Weibel's K theory, Weibel's K book. And for this first part, at least, I feel like Rosenberg's K-theory book, algebraic K-theory book, that's also a nice starting point. That slightly old Weibel's K book came out like in its full version in 2013. And it's available for free online. Yeah, it's an excellent book of around 600 pages, and it covers lots of things on algebraic K-theory, as well as some introduction to topological K-theory schemes and higher K-theory as well. So roughly, algebraic K-theory is divided into two parts. If you have seen this website that Deepankar and his team have created, this algebraic K-theory has the lower K-theory part and the higher K-theory part. The lower K groups are the so-called K1, K2, and K0, K1, and K2. The higher ones are Kn for n bigger equal 3. So these lower K groups, the contribution over here, the lower K0 is due to Grothendieck. Yeah. And for these two, you can say that Bass was the main person. Hyman Bass, he was the main person who worked on K1 and K2. The names, when he was working on them, were not really K1 and K2. They were something else. But then by the end of this course, I will show you a beautiful nine-term exact sequence, which created a new question that can you extend this 9-term exact sequence into an infinite exact sequence? And that challenge was taken up by Daniel Quillen. Okay, so this challenge was taken up by Daniel Quillen, for which he won a Fields Medal in 1978. So it's a very groundbreaking work. And what is the basic philosophy of this? I mean, generally, if you have studied, like all of you have studied different branches of mathematics, so algebra, analysis, topology. So out of them, algebra seems to be the simplest thing. Even in algebra, we understand linear spaces like vector spaces the most. So algebra is usually considered simpler than the complexity of, let's say, topological spaces or Hilbert spaces or Banach spaces. So whatever things we study, algebra is considerably simple. And for that reason, we try to associate invariants to spaces, yeah, for the purpose of classification. Invariants are introduced for classifications, and generally these invariants are algebraic. One simple example, if you want to consider, is you can associate to a topological space, a base topological space, pointed topological space, a group. Yeah, you call this group a fundamental group. Or you also associate a sequence of abelian groups, the higher homotopy groups, or you can also associate the homology groups. Those are all abelian groups. So generally, the tendency amongst mathematicians has been that you come back, like you have some space, and you try to map it to some algebraic invariants. If those two algebraic invariants are not isomorphic, then those two spaces are not similar. So this is the basic idea of classification. However, if those invariants are same, then you can't conclude anything. So obviously we lose a lot of information while we do this. Whereas what Quillen did, he went in the opposite direction, and that was the beauty of this construction. So rings are algebraic structures. Yeah, so our algebraic invariants in this case are going to classify rings according to some abelian group, a sequence of abelian groups, which we are going to call Kns. So these K groups are algebraic invariants of rings. However, when he wanted to find out these Kns for n bigger equal 3, what he did, he traveled in the reverse direction. He associated a topological space to a ring and then used the fundamental groups of that topological space to construct these KNs. And that topological space was rigged so as to match with Grothendieck and Bass's work. So that's the overall idea of what algebraic K-theory does. Yeah, so we want to find out how to associate these different groups. One more thing I want to do before we start with the actual subject is that I want to give you a big schematic picture. In no way this is a commutative diagram, but it's just a schematic picture, and it will help you until this course on algebraic K-theory ends to understand what's really going on. So here I'm just going to draw some, name some categories. So this is the category of rings. I'm not assuming commutative rings in this course. Okay, so the rings will be, rings could be non-commutative. Then this is the category of abelian groups for which we have this Kn. Then we will also have this category of homotopy equivalences classes of topological spaces. So this is the category. And here is that famous valence plus construction. So it associates to a ring, a homotopy, like a topological space up to homotopy equivalence. Then we will also encounter these symmetric monoidal categories, or in particular groupoids. We will forget about the rest of the stuff, but so here the functor is so-called the finitely generated projective modules functor. So that's the functor in this direction. Then over here we have the category of all small categories. This is the category of all skeletally small symmetric monoidal groupoids. This is the category of all skeletally small categories and functors between them. Then here it's the so-called group completion. Yeah, I mean, this is the categorical group completion construction. Then in between, we have the category of groups themselves, abelian groups, R groups, groups are categories, one object categories. From categories, you have the geometric, classifying space functor, which is called B. Then from homotopy classes of spaces, obviously you have this fundamental group functors. Over here you have HNs, yeah, the homology functors. Then over here you have the abelianization functor. Then over here you also have the category of commutative monoids, and from those commutative monoids, of course, all abelian groups are commutative monoids. So you have an inclusion over here. And on top of that, you also have one more functor, which is also the group completion. And over here, you map it to the isomorphism classes of objects. Well, I'm totally aware for those who are looking at it for the first time, this is really overwhelming, but this is just a sketch of things which you will learn in this course. There are, I should add one more thing. You can also associate to every ring, it's GL. Yeah, I'm not saying GLN. Yeah, in the next lecture, we'll see what is GL. Okay. Yeah, I mean, so far everybody has been silent, but I highly encourage you to ask questions, because again, just like looking at faces makes me feel alive. Similarly, having discussion lectures are meant to be two-way conversations, not just one way. So please do stop me whenever you have a question, and I will try my best to satisfy your curiosity. Okay, so any questions? Fine. So let us start. So the first thing, first thing I'm going to start with is somewhere here, yeah, commutative monoids and abelian groups. That's where we have. So does anybody want to tell me what is a semi-group? Yes, please. Well, it can't be the case that you don't know what a semigroup is. You have studied group theory at least. You don't need permission to unmute yourself. Just do it and speak.
A set with an associative operation.
Yes, it's a set with an associative operation. Very good. So let's say our set is S and plus is association. Now, semigroup doesn't necessarily have an identity for this operation. And it also doesn't necessarily have an inverse for this operation. So, for example, like just associativity is enough. If you add the existence of an identity, then S plus E, let's say, or 0, where anything is fine. So that becomes a monoid. And if you also add inverses, so S plus minus and E, then you get a group. Okay. So one standard example of a semigroup is that of natural numbers with respect to addition. Yeah, so natural numbers with respect to addition. Well, it's automatically, I'm also a logician by training, so my natural numbers will always include 0. If I want to say that something otherwise, then I will say that explicitly. And n plus with multiplication and 1 is also a semigroup. N plus means positive natural numbers. Similarly, n with multiplication and 1 is also a semigroup. In fact, every linear order, any linear order L with respect to min or max operation is also a semigroup. Yes, do you agree with that? It is an associative operation. It's also idempotent on top of that, but that's extra property. So we don't want to worry about that. So linear order with respect to min or max operation, which can be generalized to a semilattice. So let's say we are talking about a meet semilattice with respect to meet operation, or a join semilattice with respect to a join operation. That's also a semigroup. And linear orders are just a special case of them. Okay. We have got several examples of semigroups, and as Kronecker has said, God gave us natural numbers. Everything else was created by humans. So natural numbers were given to us, and the next thing that we study as children, yeah, that was also part of my abstract, that we go back to childhood. We could understand 2 plus 3 is 5, but then what was 5 minus 6? Yeah, that takes some conceptual, like overcoming some conceptual block, right? So there are, sorry, I should check some chat. Okay, fine. Nothing useful. So if you have any questions, please stop directly. So the next numbers that we study are negative numbers. Yeah, and we are convinced that, okay, just like 1 exists, minus 1 exists, 2 exists, minus 2 exists. However, how are those integers constructed? As we grow older, we learn a construction of integers from natural numbers. And how are integers constructed? You view them as pairs of natural numbers divided by like some equivalence relation, modulo and equivalence relation. This relation is quite simple. What is the relation? A comma B, which represents A minus B, is related to C comma D if and only if A plus D is equal to B plus C. Okay. So if we define this relation and take the pairs, then we suddenly also know what is 0. Yeah, 0 is A comma A, which is same as 0 comma 0. And this is the so-called 0. A comma A is equivalent to any B comma B. And what is important here, without talking about minus operation, just using addition operation, we can still do it. Correct? Yeah, so this works fine. Then the inverse of A minus B. So inverse of AB is BA. You simply swap the position and you get this. However, yeah, I mean, if you try to repeat the same procedure in case of a general semigroup, then this tilde which is defined doesn't remain an equivalence relation. Well, it is obviously reflexive and it is symmetric, but it's not necessarily transitive. The one property of natural numbers that we use specifically here is that natural numbers are cancellative. So n plus is cancellative. So cancellative means even though it doesn't have a full subtraction operation, it still has a partially defined subtraction operation. Which means whenever A plus C is equal to B plus C, then actually we can conclude that A is equal to B. Okay, so we can subtract as long as the number is still positive, as long as the result is still positive. So that is the meaning of a cancellative semigroup. However, not all of these semigroups in our list are cancellative. For example, consider real numbers with respect to min operation. It's far from being cancellative. And for that reason, actually, we need to modify our situation slightly. So we will define, so for S plus, define tilde on S cross S as follows. So we'll say that A comma B is related to C comma D if and only if there exists some T such that A plus D plus T is equal to B plus C plus T. Oh, sorry, I forgot to mention that all our semigroups should be commutative. Yeah, we are expecting this property. Otherwise, nothing will make sense here. Yeah, A plus D and D plus A, they will not make sense. Reflexivity, symmetry will also fail in that case. Reflexivity will also fail. So therefore, we have to consider commutative semigroups or commutative monoids. So we add this extra fluffy parameter. Yeah, there exists some T. We don't know what it is, but there exists a T such that A plus D plus T is equal to B plus C plus T. So this is called the so-called stable equivalence. Stable equality or stable equivalence, whatever you prefer. So two pairs are equal if they are stably equal. Now try to do a quick computation. Yeah, so if consider our semigroup is that of real numbers with respect to min operation. Yeah, then can you tell me which pairs are equivalent to each other under this relation?
All pairs.
Exactly. All pairs are stably equivalent. Yeah. So for a linear order, for L comma min, yeah, all pairs AB is equivalent to CD for all AB and for all ABCD in L. The same thing is true for semilattices. Okay, so actually a lot of collapsing is happening. If we did this process, like if we added this T in the case of natural numbers, then because of cancellativity, nothing happens. It's same as the previous equivalence relation. And therefore, these pairs modulo equivalence relation will form integers. However, for a linear order, if you take pairs modulo equivalence relation, then it's just singleton. So this is the so-called group completion of a semigroup. So group completion of S denoted GS is defined to be S cross S quotiented out by this relation. Obviously, you can add pairs, yeah? A comma B and C comma D, you can add pairs, pairwise, A plus C and B plus D. Because A comma B is supposed to stand for A minus B. So you can simply collect all the positive coefficients, negative coefficients, and you can do this. And this group completion actually also behaves well with respect to homomorphisms. So if you take the category of commutative semigroups, then you will land inside abelian groups. So this is actually a functor. Yeah, this is easy to verify. I mean, I'm sorry, but I cannot start talking about category theory here. I hope that everybody is familiar with at least bits and pieces of that. Yeah, so this group completion is actually a functor from commutative semigroups to abelian groups. So in particular, commutative monoids are also contained inside here. So they will also give you the associated group completion. You can verify that G of n. Yes, Nagarjuna? Nagarjuna, please talk to me. Yes? You are not audible. Okay, so whenever you are audible, or you can write your question in that case. So G of n is equal to, I mean, n plus, yeah, I should say n plus specifically is that.
Nagarjuna,
sorry? Dipankar, you are mute yourself. So G of n plus is Z plus, okay? Then can you tell me what is G of n plus with respect to multiplication? Any guesses? So we have to add
rational numbers.
Are negative rational numbers going to be in there?
No, positive rational numbers.
Exactly, exactly. So Q plus with respect to multiplication. Now, what is G of n with multiplication? I already said L with min or max is 0, but what is G of n with multiplication? 0 or trivial group?
The zero group.
Yes. Exactly.
Is it the zero group?
Yes, yes. It's multiplicative zero group. Yeah, I mean, this is also isomorphic to 0. Because there is an absorbing element. 0 is an absorbing element. Anything multiplied by 0 is 0. So 0 acts like an absorbing element. In case of natural numbers, let's say we considered natural numbers and formally added infinity. Okay. So if you add infinity to natural numbers, then what will happen? Anything plus infinity is infinity. So infinity is an absorbing element. Which means, again, for that semigroup also, the corresponding group completion is trivial. So everything collapses. Okay. So now, let me see if I have any other examples. Okay. So, in fact, we also have a map. Yeah. So from S, we have a map to GS. What happens here? Where will you send an element A to? Any guesses? A should really go to itself. But where are we mapping it to? Okay.
Class of A comma 0?
Now that's interesting. You are saying that a semigroup doesn't necessarily have a 0.
Yeah. Yes.
For a monoid, that's true. However, for a semigroup, that need not be true. So we map it to the equivalence class of A plus A comma A.
Okay.
Okay. So that's our idea. And in fact, yeah, if you are given any abelian group A and you are given a semigroup homomorphism from S to A, then there exists a unique factorization F tilde from GS to A. Well, in fancy words, in category theoretic language, we can say that this means that G is a left adjoint to the inclusion functor. Okay, so inclusion functor is, let me write it properly. So if you have commutative semigroups and abelian groups, so abelian groups are naturally included inside commutative semigroups. So in this direction, we have the group completion functor, and this is a left adjoint to that. Okay, so this universal property makes it the unique group completion. Well, what does F tilde do? Yes.
I have a question. So
Yes.
G functor. So we can say GS is the co-limit of G functor.
Co-limit of the functor. Why do you want to, like, for co-limit you had to first describe a diagram.
Yeah.
Yeah. So which diagram are you talking about?
So diagram is the S. If you are thinking about diagram of functor, so S is going to GS.
No.
G is the diagram.
It's not a diagram of functor. Yeah. Co-limit.
So
is
you are talking
always,
about morphisms.
Yes. Yeah. Simple. Simple
Okay.
thing.
Okay.
Yeah.
Okay.
Yeah.
Okay.
Yeah,
So
yeah. Okay. So if F is taking an element of A to FA, then in general, like, what does this do? If you are taking a pair A comma B, the equivalence class, then it will map it to FA minus FB. Yeah. So in an abelian group, we can always do subtraction. So that's possible. Yeah. AB mapping to FA minus FB. So that's simple. Right. So the group completion sends an element of the semigroup to the class of A plus A comma A. Now this class is, if you write this class in German, then it is the word Klasse. And this K is what Grothendieck used to denote K theory. Okay, so the word Klasse, I mean, you are associating to a semigroup its class in the smallest possible group, which is obtained by formally adding inverses of that operation. So this is the origin of the word K in of the letter K in K theory. Okay. Any questions so far? Yeah.
Yeah. So A here is an abelian group, is it?
Yes, A is an abelian group. Yes.
Okay. Thank you.
Yes. So this side is in abelian groups, and this is a semigroup. S is a semigroup. Okay. So in fact, this map, I mean, let me call this IS. Yeah. So IS, you can check this for yourself. IS is injective if and only if S is cancellative. Yeah, for natural numbers embed into integers, and that's a an inclusion, obviously. Okay. Under this, if you start with an abelian group, yeah, so an abelian group, the group completion of that is again A itself, isomorphic to A. Nothing will happen, nothing will change. Okay, so there is one more thing which I want to talk about semi-groups before we move on to some higher algebra like modules and rings. And that is cofinality. Okay, the word cofinal, yeah, means going to the end together. I mean, it sounds like some vows, but cofinality is when you have something unbounded, yeah, then you keep meeting things from a smaller subset on your way. So let me write this. Given T, a sub-semi group of S, yeah, say that T is cofinal in S if for all S in S, there exists an S prime in S such that S plus S prime A lies in T. Okay, so this is actually like cofinality is actually an order theoretic concept. So for example, Euclid's theorem on infinitude of primes, it says that there are infinitely many primes, which means, in other words, there are, like, for any given natural number, there is a prime bigger than that. Yeah, that is cofinality. Like, the sequence of primes has the same limit as the sequence of natural numbers. Okay, so here, instead of that, we are looking at addition. So for example, you consider natural numbers and all multiples of 3 inside natural numbers. Then obviously this property is satisfied. It is still cofinal. So one thing, so whenever, I mean, this is cofinality theorem, I'm just going to write the simple version of it. We'll see some examples later on. So cofinality theorem says that if T in S is cofinal, then first of all, G of T is a subgroup of G of S. Yeah, the Grothendieck group of T is a subgroup of Grothendieck group of S. This is the first property. Second property is that whenever, so if M and M prime are 2 elements in S and their classes, yeah, I mean, this is the corresponding class. I'm not going to, so this is the notation. Yeah, I mean, I'm just going to write a bracket for that. If their classes are equal, then there exists an N in T such that M plus N is equal to M prime plus N. So they are stably equal by an element of the cofinal subset, cofinal sub-semi group. And third thing, every element of G of T, G of S can be written as M minus N for some M in S and N in T. Okay, so these are all very easy to check properties. You can do that at home. So cofinality is actually quite useful when we are studying K3D because we'll frequently encounter the smaller sub-semi groups or sub-monoids. Any
Hello?
questions so far? Yes, yes. Yes, Rupkatha?
Yeah. So, yes, regarding the very first proposition here
Uh-huh.
in the cofinality theorem. So, if T is contained, I mean, even if T is not cofinal, won't this
Uh-huh.
result hold?
No, no.
Oh.
Try that.
Okay.
Yeah, cofinality is necessary to get a subgroup. Yeah, this won't always happen. Semigroups are actually very weird objects. Yeah, we don't realize it. Groups are much nicer than semigroups because of inverse, and yeah, you can start anywhere. Yeah, groups have this, have these symmetries inbuilt in it. The group acts on itself, whereas semigroup, it's not the same. Yeah, you can start at a different point and everything changes. Yes, there is something. Yes, Ganpati, can you please repeat the example of cofinal monoid? Yeah. Yeah, so 3n and n. So can you see that given any element, let's say I'm given 5. So 5 is in S, is in natural numbers. Then there exists 4 in natural numbers such that 5 plus 4 is 9, which is in 3n. Yeah, I hope that's simple enough.
Yeah, thanks.
Okay.
Sir?
Oh, yes.
Sir, if we restrict our attention to cancellative semigroups, then also the first property will not be true in general.
Oh, cancellative semigroups things are very nice. So yeah, you'll get that. But I don't want to make a general statement that if you take a sub-semigroup, then you will get a subgroup. The group completion is a subgroup. That's not true. I cannot think of an example right now, but I will tell you.
Thank you.
Okay. So let's proceed now. So once we have seen something like this, then we should also look for a source of commutative semigroups or commutative monoids. So that source is again another vertex in the diagram which I drew on slide number 2. That is symmetric monoidal categories. Yeah, I'm not going to say much about them, but just for people who know more about category theory, this is categorification of the concept of a monoid, of a commutative monoid. Okay, categorification usually means that once you are given one element, you replace elements with objects, then equality with isomorphisms. And then certain two things are equal that you replace by, so for example, our simple thing is in symmetric monoidal categories, we will have something like this, that if our operation is, oh, I should first describe what is operation. Okay, so generally these things are written like this. So S is a category. It is equipped with a functor. I'm using a tensor product notation, although this doesn't mean anything. It's just a bifunctor from S cross S to S. It's a functor in both variables. That's why a bifunctor. Then there is a particular fixed object in S. And this is not all. I mean, this will simply look like a monoid, yeah? It's a binary operation is replaced by a bifunctor, then an element is replaced by an object. However, the data is not yet complete. You will have a left identity, then you will have a right identity, then you will have something to do with associativity. So these are all natural transformations, associativity and also commutativity. We need a commutativity, so let me call that mu. So you'll have lots of diagrams. So for example, I'll just say what this is. So A tensor B to B tensor A. Yeah, I mean, these are two different objects in that category. It doesn't mean anything. You will have an isomorphism labeled mu AB. Yeah. So instead of equality, we will have isomorphisms, and appropriately the commutative diagrams, usual commutative diagrams are replaced by so usual equalities are replaced by commutative diagrams. I'm not going to go into details, but symmetric monoidal categories whose underlying category S is small or skeletally small, which means they only form isomorphism classes form a set. Yeah. So whenever that happens, so if S tensor ... is a symmetric monoidal category, and the collection of the isomorphism classes, which I'm going to denote like this, if S iso, the set of the collection of isomorphism classes is a set. Yeah, I mean, it can be a set or it can be larger than a set. It can be a proper class. So we don't want that because we want to do algebra. Algebra is only done with sets with some operations on it. So S iso is a set, then S iso, then replace this tensor with the tensor restricted to isomorphism classes, and then the isomorphism class of E is a commutative monoid. Okay, so this is a rich source of examples for commutative monoids. Whenever you are given a skeletally small symmetric monoidal category, then you get a commutative monoid. Those who have never seen this, I will try to give you some examples. Suppose you consider the category of finite sets, okay, with respect to disjoint union as the bifunctor and empty set as the corresponding identity object. Then this becomes a symmetric monoidal category. You can check all the axioms, you can go through the process, but if you apply this, I mean, a blank iso, all the isomorphism classes. So the isomorphism classes of finite sets are nothing but natural numbers. Then disjoint union of two finite sets, that becomes addition. And the empty set has cardinality 0. So the corresponding monoid that you obtain is n plus 0. So in some sense, this is some object living upstairs. Yeah, n plus 0 is very simple to deal with, but then each natural number is replaced by many of its isomorphic copies. Right? So this is one simple example. Then in a similar way, we can talk about finite dimensional vector spaces over a field K with respect to direct sum as operation. Linear algebra is familiar to everybody. So, and 0 as the 0 space as the object, 0-dimensional vector space as the unique object, which is identity in here. Then after taking isomorphism classes, you will again get n plus 0. These are two different things, but they map to the same thing. Finite sets and finite dimensional vector spaces. In general, if you have any small category with respect and which has products and terminal object, then also you get this. So there are, or co-products and initial object, then also you will get this. So you just need smallness to land inside the category of commutative monoids. Okay, any questions so far? Yes, somebody is trying to say. Shubhajit?
Just the category being Cartesian suffices, right? We don't need all products.
Yeah, Cartesian, yeah, finite products. Yeah. just need finite products, correct? Yes, anything else? Okay. Right. So these symmetric monoidal categories, if at all there are no morphisms in this category, which are not isomorphisms. So a category where all morphisms are isos, which means they have two-sided inverse, are known as groupoids. Yeah, so symmetric monoidal groupoid is another name for symmetric monoidal categories whose underlying category doesn't have any non-isomorphisms inside. So far, I will go back to the slide where I started. From rings, we have to come to this symmetric monoidal groupoids. And we have seen this map, symmetric monoidal groupoids. Take the isomorphism classes, land inside commutative monoids. Then for commutative monoids, we have seen the group completion functor. Abelian groups are naturally commutative monoids. The abelianization functor. Okay. So this is how far we have reached. So let's move ahead. I mean, this was a functor from symmetric monoidal groupoids to commutative monoids, or symmetric monoidal categories to commutative monoids. Okay, so now we have to enter our actual subject, which is algebraic K-theory. Yeah, although the flavor will be more about K-theory, I will try to give you lots of examples. However, I will try to avoid giving detailed proofs. I will only give you sketches of proofs. Because the subject, we don't want to study algebra. We don't want to study a particular class of rings. Right? We don't want to study only modules over something. We want to understand the K-theoretic aspect of the process. Okay, so I'm just going to call it a primer on rings and modules. This could be boring for those who already know these things, but I'm not sure the background is mixed. The audience is non-homogeneous, so I have to say something about this. So for me, rings are not necessarily commutative, but they have identity. Yeah, unless specified otherwise. In the next lecture, we will definitely see some examples of rings without identity. But yeah, generally we will assign, will expect identity to be present, multiplicative identity. Then modules are right modules. So I want to emphasize that many of you might have done only a commutative algebra course and all your rings are commutative. So right modules, left modules doesn't really make any difference. But here we are going to be very specific about this. Okay, so modules are right modules and the category of right modules is denoted mod R. If I'm writing the scalars on the right, it's right modules, R mod is left modules. And as a consequence, the homomorphisms are written on the left. Okay. So modules are right modules, homomorphisms are on the left. And well, I will expect you to know this, or at least go back and check if this is a ring homomorphism, which means a morphism which preserves addition, multiplication, 0 as well as 1. Yeah, this is really important. If this is a ring homomorphism, so then it induces functors from mod R to mod S and in the reverse direction. So there are these 3 functors. So the one functor in this direction is the restriction of scalars. Restriction of scalars, it simply says that, okay, if you are so if you have any n module, ns, yeah, so if you have n in ns and r in r, then how do you define n dot r? Well, n dot r is defined to be n dot f of r. This is restriction of scalars. Okay, so you induce the action of, you restrict the action of S to the action of R via the ring homomorphism F. Well, over here, you have this functor, which is blank tensor. This is the tensor product functor over a bimodule. So S is naturally a left R module via F. So this is a this is extension of scalars, and this is co-restriction of scalars. And here we will take home. And well, okay, I did not specify the directions. So home and blank. So S blank, where I have to be very specific. I want S action here and R action here, and home is taken over R. Okay, so this is a co-restriction functor, and we have got these adjoints. Okay, so extension of scalars is a left adjoint to restriction of scalars. Restriction is left adjoint to co-restriction. Okay, so why are these things important? Well, we'll also need tensor product of tensor products and home functors. They behave nicely with respect to each other. So there is home tensor adjunction. And in one single line, I'm going to say this. So this is home MR. Yeah, this is a left R module. Tensor over R with a bimodule. And here I'm taking home over S. This is naturally isomorphic to home over R of MR and the home over S of NRS PS. So this is a different. If I have this bimodule, then this tensor functor is a left adjoint to home S, NRS blank. Okay, so this is again something standard. If you want to learn K theory, yeah, K theory is usually taught as a graduate level course, then you should know rings and modules. And I'm giving you pointers. If you have never seen this, then these are the pointers, these are the things you need to know. Okay. So in general, if you look at this, then tensor products are not necessarily, so mod R tens cross R mod. Yeah, if you take a left module and a right module, so MR comma Rn, from here you actually go to abelian groups. Yeah, you map it to MR tensor over R of NR. This tensor sign actually takes R inside. So you just map it to abelian groups. Those who have seen commutative algebra, yeah, for them this result is also in the same category, mod R cross mod R to mod R. However, in the case of non-abelian, non-commutative rings, that's not necessarily true. However, one thing extra we can have is, instead of this, if you take that there is this S mod R, bimodules over here and bimodules over here, then you will land inside S mod T. Okay, so that's the difference. Okay, let me change the color back. Okay, so this is something we will need. And one more concept that we will need is that of, what happens when you have adjoints, yeah? So these tensor products are like tensor functors are left adjoints, and left adjoints are right exact, which means they preserve co-limits, and the right adjoints are left exact, which means they preserve limits. So Rex, in other words, it says that it behaves well with respect to direct sums. It preserves direct sums, direct limits, and co-kernels. Whereas over here, you will need direct products, inverse limits, and kernels. Okay, so this is basic category theory again. We will need these things. Okay, the next concept that we want to encounter is that of a free module. Free modules are natural generalizations of vector spaces. Yeah, the property of vector spaces is that if you are given a field, then you start with you define the concept of linear independence and spanning. So if both of those conditions are satisfied, then you get a basis for your vector space. It is a subset. Basis of a vector space is a subset which is both linearly independent and spanning. Now the same thing is true in case of free modules. Not every module is free, right? But free modules have a basis. Yeah, have a basis. Yeah, all the free modules actually look like this. If our ring is R, then all the free modules look like direct sums of copies of R. Those could be finite direct sums or infinite direct sums, but these are always direct sums, which means you would start talking about tuples which are zero almost everywhere, zero except for finitely many places. So those are free modules precisely and nothing else. Now, one property when you write this is that once you consider this, then this is isomorphic to the disjoint union of this, which means free modules are closed under direct sums. Well, zero is a free module. Free modules are closed under direct sum, and therefore we can talk about free finitely generated free modules over R. And that category, the full subcategory of the module category, will denote by free R, which turns out to be a symmetric monodal category with respect to direct sum operation. Okay, so free modules with direct sum and zero as the identity. Now, obviously, you know that zero is the identity for direct sum operation. So we have this symmetric monodal category. And from here, we can start asking questions. Like I said, why finitely generated? I said finitely generated, but you might ask me why finitely generated. The answer lies in the explanation that I gave earlier. if you start talking about, let's say, a countably infinite module, countably generated, yeah, countably infinite module, and then you are talking about Rn direct sum this, what will it be? Yes,
it will
R
be the same
infinity
module.
again. Exactly, R infinity. So which means R infinity or any infinite thing is going to behave like, even if you add just the smallest infinity thing, then it's going to start behaving like an absorbing element. So everything is stably equivalent to R infinity, and therefore we don't want to deal with. Saurav, I think this lecture is being recorded, so you don't need to get PDF notes of this lecture. Yeah, that it will be available on YouTube. If I'm, yeah, I can see the recording, son.
Yeah, we will have the recording as well as notes.
Yes. Okay. I will also give you notes afterwards. So therefore, we should not deal with, when we want to do algebra, we should not include infinities. Yeah, ordinal arithmetic is only an exception where we actually deal with infinities. Otherwise, we don't really deal with infinity and algebra. They don't go hand in hand. Okay, so that's why we wanted to talk about finitely generated free modules. However, now is free really enough? I mean, in most cases, consider a commutative ring. Yeah, for commutative rings, if we start talking about this free R, yeah, I mean, what's going to happen here? One free module for each rank. Yeah, we don't use the word dimension in the case of modules, we use the word rank. So one free module of each rank. So obviously the isomorphism classes of free modules over a commutative ring, that's going to turn out to be something boring, just natural numbers, and we cannot get any information, cannot extract any information out of it. However, now the key is that we want to keep finitely generated and we want direct sum as our operation. So we will try to include more things if possible, more modules in this collection if possible. And those so-called more modules are known as the projective modules. So this is actually the main object of study in algebraic theory. So when do you say a module is projective? So say that P in mod R is projective if there exists another module Q in mod R such that P direct sum Q is free. So we are not looking outside, we are looking inside. We are trying to close the free modules under their direct summands. Right? So if there exists some other module such that this happens, P direct sum Q is free, then we say it is projective. And in particular, if it is projective as well as finitely generated, which means if I can add over here finitely generated, then I will denote the corresponding category of those modules by Proj R. A quick calculation, a quick calculation will show you that direct sum. So if P1 and P2 are two projective modules, then P1 direct sum P2 is also projective because P1 will have some Q1 and P2 will have some Q2, and then their direct sums, after rearranging its direct sum, is associative, commutative, everything nice, for which we needed that symmetric monoidal property. So everything is nice and this will turn out to be free. So therefore, projective modules are also closed under direct sums. And when you restrict to finitely generated, then also it is closed under direct sum. And zero is again projective. So free modules are obviously projective. Yeah, for if P is free, then you can take Q to be 0. So that P direct sum Q is free. Okay, so if you have understood this part now, so I can actually claim that this is my main object of study. That Proj R, then direct sum with 0. And if I take its isomorphism classes, then I will get a semigroup, a commutative monoid. And if I take its group completion, then whatever is the result, I will denote it by K0 of R. Yeah, this is the so-called Grothendieck group of the ring R. Okay, so because we wanted to avoid having an absorbing element, we tried to avoid infinity, so only finitely generated projective modules. So in other words, isomorphism classes of finitely generated projective modules. Okay, one thing, like what is the connection between free R and Proj R? Any guesses?
Prior is the cofinal in projective.
Exactly, very good. So pre-R is cofinal. I mean, in the language of categories also you can define cofinality. Yeah, instead of equality, you replace it with isomorphism. So free R is cofinal in Proj R. So definitely we will have more information in finitely generated projective modules than that is present in free R. Okay, so therefore this is our new thing. So Grothendieck introduced this construction. Yeah, I mean, there are different ways of constructing Grothendieck groups, not just this one. You can also describe it using generators and relations, let's say via exact sequences. However, we are not going to go into that part yet. The important thing is Grothendieck did this in its far-reaching generalization of Riemann-Roch theorem. It is now known as Grothendieck-Riemann-Roch theorem. And the idea, I mean, which was interpreted later as doing linear algebra or dimension theory over finitely generated modules. Yeah, I mean, doing dimension theory is the purpose of this. Like I'll show you the particular category. Yeah, if you talk about finite dimensional vector spaces, then dimension is precisely this map. Every vector space maps to its dimension, which is a natural number. So we wanted to do dimension theory like linear algebra and dimension theory over arbitrary ring. And then what is the corresponding class? What is the dimension of a projective module? Well, that dimension is nothing but this. Every projective module will, like if P is in Proj R, then it will be associated to its corresponding class in K0R. Okay, so this corresponding class is the dimension. Yes, so Saurav, why we consider P as a prime ideal of A, not as a composite number or imaginary? I'm not sure how I can answer this question. And I don't even know the relevance of this.
Saurabh, can you speak up and say your question? Maybe you can clarify it a bit.
Whenever he can. Yeah. So the corresponding class of this is the so-called dimension of the projective module. He's writing why we don't use complex numbers instead of primes. how is this relevant to our what we are going to like what we are doing right now? That's not clear to me, Saurabh. Okay. Yeah, perhaps if you could speak, then you can clarify what you are saying. Anyway, so come back to this. So every projective module has a dimension. And this is the best possible way we can do it. So far I have described to you these functors. Yeah, this particular functor. So now we know what is K0. K0 is this direct connection which commutes with this, and this. Okay, that's our path to define K0. Okay,
Sir?
some properties about, yes, somebody's
Sir,
talking.
to study the dimension theory of projective modules, why are we not
Uh-huh.
going into rank of the projective module?
We can and we will at some point, but rank of a projective module is not always well defined.
Yeah.
Yeah.
I mean,
So,
so
if you already know that, then you know the answer as well.
I mean, will it be true that if it is a constant rank, then your notion of dimension and this rank will match?
I think so, yes. I mean, it will simply be a number, whereas this one is not just a number. If every projective module has a number like numeral rank, then it will agree with that. Yes. Okay. However, yeah, I mean, others should not get confused. So he was asking the question about a rank function, which is not yet defined by us. Yeah. So we'll have to wait. Yeah, I will talk about that particular rank function later. Yeah. The only rank that we know currently is that every free module has a basis. So every free module has a rank, if it can be well defined. So I want to talk about some of the properties of projective modules. So a module is projective if and only if the following are equivalent. Yeah. First one is that PR is projective. I will always write this whenever possible to denote the sign of like whether it is a left module or a right module. Then the second property is that home PR, like home R blank, is exact. Okay, so in other words, if you are given a short exact sequence 0 ABC 0, then so is the exact sequence home PA, home PV, and to home PC. So this particular sequence is always exact. I mean 0 home PA, home PV, home PC. The thing that we can't generally add is this last 0. But if P is projective, then we can add that last 0. Yeah, which means this map is also surjective. Well, rewriting this, whenever you have a short exact sequence like this, and if you have a morphism over here, then there exists an extension from P to B such that this triangle commutes. Okay. Fourth one is that if 0 A B P is exact, then it is split exact. Which means every module homomorphism with P as a target splits. Okay, so this is also yet another equivalent property. And yeah, right now I just want to talk about these 4, 2 and 3. I mean, these are all, this is a standard exercise in a ring theory or module theory course. I think there are some comments. Okay, so you can perhaps write to me later. Yeah. Fine. Okay. So the projective modules have different characterizations. These are like, let's say 2, 3 and 4 are homological criteria for it being projective. But nevertheless, they are very easy to check criteria. All 3 modules are projective, so you have some examples. Another thing which I can say that if P is projective, then of course home PR blank is exact, but this one is also exact. Is also exact on left modules. Yeah, so in other words, this is flat. And one more thing that we know is tensor products and direct sums, they behave nicely because tensor product functor is a left adjoint. So they behave nicely with respect to each other. So, okay. Yeah, I should first say something. K0 is a functor.
Maybe you need peer dual tensor.
Dual what?
I
I said on left modules. On left modules, this
okay,
is
okay.
Yes.
Oh,
yes. Yeah. So, let me talk about the functoriality. It also behaves nicely with respect to morphisms. So whenever you have a ring homomorphism from R to S, then correspondingly you have a strict monoidal functor from proj R to proj S. Yeah. If this is F, then you have proj F. Then correspondingly you have a map between their isomorphism classes. And hence there is a map. Okay. My tablet is not letting me write good handwriting. Anyway, so these are all assignments which are functorial, and hence the entire assignment is also functorial. So in general, K0 is a functor from rings to abelian groups. However, there is something which we did not talk about yet. Like if we had a commutative, like a semi-ring, a commutative semi-ring. So commutative semi-ring is an object of this form, S plus dot, where S plus is a semigroup, S dot is also a semigroup, and dot distributes over addition. Same thing as ring, but we don't expect additive inverses. So that's a semi-ring, and the plus operation is commutative, then it's a commutative semi-ring, and multiplication is also commutative, let's assume. So in this case, the multiplication of those classes, if you remember the classes AB tilde, so this is A minus B. Yeah, you can also multiply this class with the class of CD, which we already do in the case of natural numbers, and this multiplication is defined to be, well, this is A minus B, this is C minus D, so this will be AC plus BD and AD plus BC, the equivalence class of this. So the multiplication is also well behaved on those pairs. So the multiplication also passes on to the corresponding group completion, which means from a commutative semi-ring, we get a ring, a commutative ring. Okay. So if we had a semi-group gave us an abelian group, But if we had a commutative semiring, another operation, then that operation behaves well, and we also get a ring structure on this abelian group. And because of that, in particular for commutative rings, this K0 functor restricts to a functor from commutative rings to commutative rings, because the corresponding result is also a ring. Okay, so what is the operation here? Well, Proj R, so if, sorry, I should say something, erase this. If R is commutative, R is commutative, sorry. Then Proj R, direct sum 0, this is a symmetric monadal category. On top of that, there is a tensor operation with respect to, and which you have an identity, namely the free module of rank 1. Yeah, RR. This free module is the identity with respect to this, and tensor product distributes over direct sum. So therefore, the corresponding isomorphism classes become have a semiring structure, commutative semiring structure, from which we get a ring. K0 becomes a ring.
Sorry to interrupt you, Professor. Just sort of running out of time. We shall wrap up maybe a few minutes.
Yes, we will wrap up in 5 minutes. Yes, so this is a tensor product is called in this case a pairing. A pairing is another bifunctor which distributes over your usual operation. And therefore, K0 of R is a ring. Yeah, this ring is called the Grothendieck ring. So Grothendieck group for all rings and Grothendieck ring for commutative rings. Okay, I will only do one example, yeah, one simple example, that is of projective modules over a field. Can you tell me what are projective modules over a field?
All vector spaces.
Yes. All vector spaces. So there is nothing else. And vector space, what are the isomorphism classes of vector space?
Natural numbers. Cardinals.
Yes, natural numbers. So therefore, we will get just natural numbers, finite ordinals, whose group completion we have already computed. Yes. So therefore, for Proj K, I shouldn't even have written this particular part. I should say that K0 of a field is isomorphic to K0 of a division ring. Yeah, there also you can do dimension theory as usual. So this is isomorphic to Z. Okay. So there was one question in from the audience that how is the functor defined? Yes, I forgot to mention that. If you have this particular thing, yeah. So this functor is the extension of scalar's functor. Yeah, this is blank tensor over R with the bimodule SRS. Yeah, you can verify that when you take projective module, you actually get a projective module. It's tensor. Its extension is also projective. These are all things to check. Yeah, I'm not saying this is easy or anything, but yeah, this is the functor. I should have said that earlier. Okay, so next time we will, so now we are wrapping up. So next time we'll see that for many known classes of rings, like let's say PIDs, local rings, the answer is again going to be Z. The Grothendieck group is again going to be Z. The interesting examples, however, come later. So for example, in algebraic number theory, people study Dedekind domains So for Dedekind domains, we will get a non-trivial example of K0. We will also see next time some property known as IBP, invariant basis property. And what is its connection with free modules and Eilenberg-Swindle? Yeah. So Eilenberg-Swindle will also be constructed next time, and that's like why Swindle means fraud. Yeah. Why infinite dimensional modules are fraudulous in this case. So that's the point of Eilenberg-Swindle. So Ganpati's question was, can we say isomorphism classes of Projar form a set? Yes, because we have taken finitely generated. So finitely generated, I will, so a module M is finitely generated if and only if you have some N and this kind of exact sequence. Okay, for some N. Now, how many quotients of R to the N can you take? Well, a set many. And when you take this union, countable union of sets, it's again going to be a set. Yeah, so that's why finitely generated modules themselves form a set up to isomorphism classes. Okay, so this is, yeah, I mean, now it's open for questions. If you have any questions, please do ask.
Sir,
yeah.
This K0 field, this is Z for any characteristic field, or like it is only for characteristic?
Yes. Field's characteristic is irrelevant. It identifies lot of things.
Okay. Thank you very much, sir.
Okay. Any other questions? Yeah.
Hello.
Yeah.
So you said that for a field K, the proj, I guess you said it, the proj K.
Proj K, yeah.
Yes, that will be the like all vector spaces over that field K.
All finite dimensional vector spaces. Yeah, I mean, we need finite generation. So this will be simply finite dimensional vector spaces.
Yeah, that was my doubt.
Yeah. Yes. Any other questions?
Sir?
Yes. Yeah.
Sir, can we characterize the class of heading R for which K0R is isomorphic to Z?
No.
Oh. So in particular, in
there
other
will be
example,
many.
Instead of field or division ring?
Instead of what?
Field or division ring, can we have another example for which?
Oh, yeah. We will have PIDs. K0 of Z will be Z. K0 of any Laurent polynomial rings is Z. Sorry, yeah. There are so many examples. Even if you take polynomial ring over a PID, yeah, like something like ZX, that's also Z. So K0 actually identifies lots of things. Yeah, it doesn't classify between them.
Okay.
That's Quillen-Suslin theorem. So there are big results about this, and there are many great mathematicians, even in India, working on algebraic K theory. And the computation of one K0, like K0, K1, K2, that's not an easy job. If you have seen algebraic topology, that computation of fundamental groups is hard. Yeah, similarly, computation of K groups is also hard. Yeah, I mean, I can say that for model theoretic setting, main part of my PhD thesis was to compute K0 of modules. That's all. So I got a degree based on that. So it's a non-trivial problem. So yes, we need a lot of information about projective modules. If you are doing topological K theory, then you will study vector bundles instead of projective modules. Yeah, there are different things which we study, but underlying philosophy is still the same. So can we give a proof of any higher dimension, which is 4th dimension? Oh, okay. So Saurav, I'm really sorry. I have no idea about physics. I'm literally a fool when it comes to physics. Yeah, I cannot really comment on anything in that direction.
Hello,
Yes,
sir.
so with this,
Yes. Yes, Ganpati.
Yeah, so here, like for showing the K0 of field is Z, basically we use the fact that all projective modules are free. So
yes.
So is the converse true that if K0 of something is?
Oh no. So if all modules, all finitely generated projective modules are stably free. Yeah, stably free means there exists. So PR is stably free. If P direct sum Rn is isomorphic to Rm for some n. If this happens, then we say that if every projective module is stably free, then K0 of R is Z. However, that's not really a characterization. Yes, Deepankar, you want to stop me now?
Yeah. So with this, we would like to end our session today. If you have any more question, you can reach out to the speaker. All the lecture materials would be.
I think Yajishi has one question.
Sure,
Let's take one.
Sure.
Sir, you mentioned that for topological K theory, you're looking at vector bundles.
Yeah.
Or for algebraic K theory, you're looking at projective modules. What do you do for what do you do for categorical K theory?
You generally look at objects. Yeah, so like projective modules are objects of a category, yeah, which carries a symmetric monodal structure. In case of vector bundles, also vector bundles of finite dimension over a fixed topological space, they will also form a symmetric monodal category. So when you are studying K theory of exact categories, then you will have a notion of exact sequence, short exact sequence. And that structure will give you, like the objects, the classes of objects will be the generators modular relations given by exact sequences. Like if 0 ABC 0 is exact sequence, then class of A plus class of C is equal to class of B. That will be the relation, and you quotient out by that. So you classify objects of a category. Yeah, so that's why categorical K theory is the most general setting.
I think it needs to figure out one have to figure out which particular objects are relevant in case of that particular category. Just as in case of algebraic K theory, you have projective modules. For a general category, you need to figure out what objects work, or otherwise you sometimes need to, get to a category where you can do K theory. I guess that's the idea.
Just as a follow-up on that, perhaps one more question. So the projective objects here in over rings or something, at least in the commutative case, they are really the cofibrant objects in a model category, right? Of the chain complexes.
What?
And so your projective modules, projective resolutions perhaps, right? These guys are the cofibrant objects in a particular derived category or in a particular model category, which is the chain. Yeah. And in the topological cases, you have like the isomorphism classes of CW complexes, which are the cofibrant objects, and these capture all spaces up to homotopy, peak homotopy equivalence at least, right? So is there some sort of notion of K theory on model categories that would
I'm not aware of this. And by the way, I don't think like even the projective resolutions fit nicely into this picture. We are only talking about projective modules, and for higher K groups, we will do something totally different. So it's said that K1, K2, Kn, all those things are orthogonal to K0. K0 is a spread, whereas K1, K2, Kn, they look at a different kind of structure. I will discuss more in next lectures. Resolutions are not relevant in this case.
Okay. Let us end our session today here, and let's thank the speaker. Thanks for this wonderful lecture. We'll see you next week, and we are really sorry about this mishap which happened due to some unknown reason. We'll try to fix this, and next time we'll make sure that such a link issue does not occur. Thank you for being here.
Sure. Well, I'm going to be here if anybody wants to talk. Yeah, those officially the session is over.
Sure.